Assalamualaikum warahmatullahi wabarakatuh and good afternoon. So this is our second session. So hopefully you guys can hear me.
Waalaikumsalam, Dr. Yes. Okay.
All right, good. Okay, so now we will move to our last chapter. So which is the other filter type, which is IIR, on how to design it. Okay, so this is a IIR filter design or infinite impulse response filter design. And what is the difference between FIR and IIR? So last time we have what is the difference? So FIR. So in terms of filter coefficient. So this one, A is equals to 1 fixed FIR. Okay. And then of course we will have B, which is equals to HN. So that's why in designing FIR filter, so what we are trying to find is HN. Because we are actually finding B, the filter coefficient B. And we doesn't need to find what is A, because A is fixed to 1. Right, so this is a fixed to 1. So that's why the equation is HN. HN equals to something sinc of something. Right, and then multiply with a window function. So that's because we are using a windowing methods. Right, for IIR filter, this one, so we have both. A, we have something. B, we have something. Right, so then the design will be, the approach will be different, right? Because we're not going to find HN. So we will find A and B. And this A and B can be represented either, these two can be represented either by HZ or a difference equation. Okay, so in designing IIR filter, so we should find difference equation. Because difference equation is the one which is in time domain. If you get HZ, this is not in time domain. This is in Z domain, right? What is HN? HN is in time domain. So because your product is supposed to be in time domain, because implementation is in time domain. So we don't do implementation in Z domain or frequency domain. Z domain and frequency domain is only for designing purpose and for analysis. For implementation, doing the filtering itself, so everything must be in time domain. So that's why in FIR we find impulse response, which is in time domain. And for IIR filter, we are trying to find difference equation. So which is in time domain, because we need to find both A and B. Okay, so that's the difference. And let's see some basic first. What is this is actually similar to what we have previously in FIR filter design slides. So then I'm not going to repeat this. Okay, the filter characteristics. So the same thing, we should have omega C, omega P, omega S, and we need to handle the transition bandwidth and ripple. Okay, this one. So the filter characteristic is the same. So it's just the method on how to get it and what will be the product. So it will be different. Okay, and in IIR filter design, so basically, I think the most common methods is we have two. One is impulse invariance, another one is bilinear transformation. But we're going to focus only on bilinear transformation. We're not going to focus on impulse invariance, right? So we're just going to look into this one, the second one, bilinear transformation. And so what is actually bilinear transformation? This is the methods. FIR, the method is what we call a windowing methods. So in this IIR, so we call it bilinear transformation. Okay, so in the bilinear transformation technique, the relationship between the S-plane and Z-plane. Okay, so now we have S-plane and Z-plane. It's shown below where C, so there's a C here, equals to 2 over TS, and TS is the time sampling. So there's a relationship, and this relationship is actually between what we call a S-plane and Z-plane. So what does this mean? So S-plane and Z-plane. So actually, basically, what we do, we are actually doing this. This is the transformation. The transformation is this relationship. So we're going to transform S plane into Z plane. Okay, and by that, it means that the S plane is actually the analog filter. The Z plane is the discrete filter or the digital filter. So in IIR filter design, what we do is we will take the established analog filter. So for example, in this course, we will use a Butterworth filter. So Butterworth filter is one of the established analog filter. And you have heard about Butterworth filter a lot previously because you have learned several filtering method in a few courses. Right, so that's why we have heard about this Butterworth filter. Let's see. So is there echo? So anyone? Let's see. I'm checking. Is someone is didn't mute? Everyone is already mute. Okay. All right. So hopefully there's no echo anymore. All right. So so actually that's the idea. Okay. The idea of an IIR filter is we take the established analog filter. So which is in this course, we will use a Butterworth filter and then convert that into a digital filter. Right, so that's actually different for FIR. FIR is what we do is we take ideal filter and then convert it into FIR filter. Because ideal filter is actually, if we convert it into HN, so it becomes a IIR filter because the sink function is actually, the range is from -infinity up to infinity. And then we put a window on it, so it becomes FIR. But IR filter, so we're not going to do that. It will not be based on ideal filter. So we take established filter from analog filter, established analog filter, and then convert it into digital filter. And in converting that, so this is actually the equation. This is the equation on converting from analog to digital filter. So which is, we have this parameter C. So this is the parameter C. So how do we convert that? So this is S is actually representing S plane. So where you do Laplace transform last time. So this is coming from the Laplace transform. And then we will convert it into Z plane. And Z plane is from Z transform. Right? So there's a little bit different between these two. And I think last time in phase 1 assignment, I think some of you, I think those who get Z plane topic, so the one that you represent is actually the analog filter, the Laplace transform, the S plane, okay, instead of the digital Z domain. Right, so make sure you didn't confuse. There is a difference. There is a difference between S plane and Z plane. The poles and zeros location are different. Right, so that's why we need to do this conversion, this transformation. Okay, so that one is instead of a Z and S. So how about between the frequency? So this is the relationship between the frequency. So this is the capital omega. This capital omega is for continuous frequency, continuous time, right? Continuous time. Actually, capital omega, small omega, both are actually continuous frequency, but this is for continuous time. Small omega, a discrete time. Okay, Z, discrete time. S, continuous time. Okay, so this is where we convert that. This is a relationship between S plane and Z plane. This is a relationship between the frequency. So we have this. So we need to manipulate this relationship so that we can convert it into. So we just take establish a Butterworth filter and then convert it into a digital filter. So that's the way to do it. And this is what we call the mapping. This is the analog filter, right? So let's say this is a Butterworth filter, and not just any Butterworth filter. This is a very special. So we call it normalized analog filter. So there's a term here, normalized. So when it is called normalized, So which part is normalized? The cutoff frequency. The normalized analog filter, the cutoff frequency is equals to 1. Okay, so why we do that? So later I will explain it. But we will take this one, the analog filter, where the cutoff frequency is fixed at omega c equals to 1, and then convert this into a digital filter. So this is where how to convert this from the analog to this digital. So you need to have that C parameter. Okay, you need that C parameter because this is the conversion between the frequency. So the y-axis doesn't change because it doesn't involve the y-axis. So we only change the frequency, the z plane and s plane. Okay, so that's why the difference here is omega c equals to 1, and this omega c is the one that's spec given to you, which is required. Okay, so between this. And this is actually just converting this digital filter so that this is omega c. You convert that omega c into a physical frequency. So this is a normal conversion of a frequency. But actually the bilinear transformation is this one, these two. Between a normalized analog filter, convert it into digital filter. All right, so that's the basic on how to do it. And this is the procedure. So we have 4 steps. So let's see. So I have this slide. Okay, all right. So let's see the steps on how to design IIR Butterworth filter. So this is actually the filter that we need to design. So always we need to find out what is the omega c. So what is the maybe omega p? We need to know that, but most important is the omega c. Okay, the omega c and then omega p, and then what is the ripple if needed. All right. So if you are given the spec that you need to make sure the ripple is low at some certain value, so you need to put that in your design. Right, so this is the filter. So most likely this is the shape. It's a transition between because we have an omega p and omega s. Right. So how to do this? How to do this? So then the first step is that one, which is specifying filter characteristic. Okay, you need to find omega c. You need to know what is the capital N, the filter order. So sometimes you need the ripple. Sometimes you need the omega p and omega s. All right, so and this one, so this is of course this plot is the magnitude response. So because when designing, so actually we are referring to the magnitude response. Where is the omega c, omega p, omega s, all those ripple? So this is actually you observe that on a magnitude response. So the first one settle, and then this is the second one. So the second one is now after you know what is the spec. This is the time to convert. This is a normalized analog filter, which is the capital omega prime. Okay, if it is just a capital omega, so maybe that one is just an analog filter. So when we have when we put this prime there, so we are actually referring to a normalized analog filter. And this normalized analog filter is the capital omega c is equals to 1. So we'll see why we need that. And this is where we need to convert this into digital filter. So where this omega, capital omega c, generally this is the equation. And then we can use this equation. Why we need this equation? Because we need to find C. We need to find C. All right. So where will we use this C? Later, that one will be on the third step. Okay, then we can use this omega. This is a general. So if you put it as a omega, capital omega prime c, so this is at cutoff frequency. This is general frequency. This is on cutoff frequency because we know the cutoff frequency is equals to 1, so we can get this equation. So equals to 1. Okay, and of course sometimes we need to use this also. We need to refer to this capital omega prime p and capital omega prime s. Okay, so if this is not enough, So maybe we need to use this, right? But generally, this is how we describe the relationship of the frequency between the analog filter, the normalized analog filter, and our discrete filter. Okay, so this is why we need to use because this is step 3. Why we need to use this normalized analog filter? Because this normalized analog filter, so we have a standard system function. Okay, so this is actually the system function that we need to convert into digital filter. So the equation is already fixed. So and this is fixed only when the cutoff frequency equals to 1. So that's why we use this normalized analog filter, so that we can just refer to this one. So if we want to have a filter of a first order, just take this equation and convert this S into Z. If we need a second order, so we just take this equation and then convert this S into Z. Okay, and so this is why in converting this, so this is actually the conversion. This is the conversion. For first order, 1 over S plus 1. So actually you will get in discrete or in digital filter, 1 plus Z minus 1 divided by D1 plus D2 Z minus 1. Okay, so we already know that. And all this table is actually, it is a standard table. It is a standard table. You doesn't need to memorize all these things also. We just need to know, okay, if the order is 1, so actually we need to get this one. So this is our filter. This is our IIR filter that we need. Right, and what should you do here? So which one is not solved is that D1 and D2. So you need to solve for D1 and D2. If you need to do a second order, so this is actually the analog filter. So the discrete filter is this one. So 1 plus Z minus 1, and then to the power of 2. So you have a B11, B12, B13 there. So you need to find what is the value of B11, B12, B13. Third order, you need to find D1, D2, B11, B12, B13. Okay, so in the, when we putting everything in steps, so what actually we do is to design an IIR butterworth filter is actually just solving this parameter, the D1, D2, B11, B12, B13, those things. Okay, and how to solve that? So this is actually the equation. So let's say you have a D1 and D2. So what is D1? D1 is 1 plus C. Okay, so what is a C? So this is a C. So this is a C. So that's why you need to solve this thing first, get what is C, and then you can solve D1. Second order, you need B11, B12, B13. So this is, if it is a B11, then the I here will be 1. So then it becomes B11. So what is the B11? B11 is C squared plus A1C plus 1. And everything, the A will be given. Actually, this A is this one, 1.4142. So that's your A. And what is the C? Again, you need to solve this one. Solve this one, you get the C. So you get C, then you can plug in the C value. You already know what is the A. A is just this one, 1.4142. Okay, and so on, and so on. For third order, you need to solve D1, D2, B11, B12, B13. Right? And last one. So of course, the last one, we need everything in time domain. So that's why after you get this HZ, so this is the HZ, and then you just convert this HZ into difference equation. That will be a very simple process. Okay, so we have done that many times before. All right, so let's see some example. Hopefully we can do, I think we have time to do at least one example today. Right, so this is actually the filter design procedure. So the one that's I have explained on a different slide, that one. And of course, in this slide, there's a lot of theoretical, conceptual parts which explain how finally we get into this form. Okay, because at the end, we just need this thing. We just need this thing and solve those parameters. So how do we get all these things? So we have all the details here. So you can read that one if you are interested in knowing the details. So if not, so you can just skip the detail and then do the design. Okay, do the design. So because most important is even if you do in MATLAB, so you just need to know what is the spec, and then you just plug in the value, and you will get your results. All right, so let's do example 1. So design a digital low pass filter based on a second order Butterworth filter. Of course, in this course, in these slides, so you will just see one type of filter, which is a Butterworth filter. So we have other types of filter. We have a Chebyshev and others, right? But we're going to focus on Butterworth. So if it is a Chebyshev, then this equation will be different because this equation is for Butterworth. So other filter will have a different equation, different system function. Okay, so what will be the spec? The spec is supposed to be a second order. So it's supposed to be second order. Then second order means a capital N equals to 2. And then the cutoff frequency is omega c equals to 0.5 pi. Right, so of course this example is quite easy because straightforward, it gives you the cutoff frequency. And even actually in real situations, so maybe this is how you do it. Okay, maybe in your even in your assignment. So how do you separate, how do you design a filter? How do you separate this noise and desired frequency? So you just pick the omega c. Okay, testing it, the omega c, and then testing it with the N, the filter order, and see whether the output will be okay, okay or not. Okay, either it is as you expected or not, right? So, but of course, we can go more detail by doing by finding the omega p, omega s, and all those ripple. But this is the basic way of designing filter. You just need to know what is the order, what is the cutoff frequency. All right, so the solution is step 1. We need to specify filter characteristics, which is already given here. Omega c is equals to 0.5 pi, and the filter order is equals to 2. And second, step 2. So if you look here, so this is actually step 2. So this is a step 1. You need to find what is the omega c and capital N. And in step 2, so you need to find that c. Right? So you need to find that c, and this is actually the relationship. Okay, and so this is actually I'm writing that relationship. So which is the capital omega prime c, which is at cutoff frequency, which is equals to c dot multiply to tangent omega c. This is the discrete cutoff frequency, discrete filter cutoff frequency, which is this one. Omega c equals to 0.5 pi divided by 2. Okay, then from here, and we know that this is actually equals to 1. Because what is this? What is this? This is the cutoff frequency of normalized analog filter. And it's already fixed equals to 1. Okay, that's why we call it normalized filter. So it is a normalized at the cutoff frequency. So, okay, so we know that this is equals to 1, then a C, that's C. So this is where we get 1, this is 1, this is 1. And then you divide by this tangent of omega c divided by 2. And that tangent omega c is 0.5 pi divided by 2, you get 0.25 pi here. And then do that, tangent of 0.25 pi, you will get 1. So 1 divided by 1 equals to 1. Okay, so then the C value is equals to 1, right? Of course, in this example, the value is quite nice. Okay, so if the cutoff frequency, let's say 0.3 pi, so maybe you're not going to get a very nice number. So you must get some floating points, some points. Okay, so maybe you get up to in exam and test. So to make it a simple, actually I allowed you to just to take up to a 2 point. Okay, it doesn't have to do up to 4 point of the floating point, right? Because it's just a number. Maybe it's not accurate, but at least you prove something. Okay, so it doesn't need a very complicated number. So then, step number three is to transform HS to HZ. Going back to here, so this is step number 3. So we need to convert this. It is a second order. We already know that from the spec. It is a second order. So from second order, so we will take this one, right? If it is a first order, you will take this one. So because this is a second order, so we will take this one. So 1 over S squared plus 1.4142 S plus 1. Right, and actually, if we look at the digital filter, so actually this is the digital filter. So what you need to do is actually find what is the B11, B12, B13. So you need to find these 3 values. Okay, then you will solve that. Then you will solve the HZ. Okay, so that will be the step 3. And but in this slide, actually this is this example is to show you how to do it, how to solve that. Originally, it is solved such this. This is the HS. Where do we get this? From this table, because it is a second order. So then, actually, this is the relationship that we have previously. Okay, the first thing that we, the one that I have shown you, we have a 2 relationship. One is on S and Z plane, and the other one is on the frequency relationship. Okay, this one. So in example 1, I try to show that if we do, this is actually the original solution. So we change every S into Z, okay, by this relationship. So what is this? This is actually after doing some, we simplified everything. Okay, we simplified everything because doing that actually is quite complicated. Changing every S. So if a second order, so you have a S squared, and then there's an S here. If it is a third order, so you have a S here, S squared here, and then another S. So if you want to do that one by one, so it becomes a very complicated maths. Okay, so actually this table is, we already skip a lot of things, we simplified things, right? So we simplified things that we doesn't have to do that, because we already know what is the shape of the HZ. So this is the form of the HZ. But just to show you that actually, first thing, actually we do that. Originally, we solve it such that. Right, so this is HS, and then replace every S with a C, 1 minus Z to the power of minus 1, 1 plus a Z to the power of minus 1. And we already know what is a C. So what is C? C is here. C is equals to 1. Okay, and then do that, replace every S. So this is the one that you will have. Okay, so solve that. So this is what I say, that this is quite a complicated maths. Right, so a lot of parameter, a lot of numbers. So in one equation, so a lot of terms. So 1, 2, 3, 4, 5, 6, a lot of things. Okay, so but we can do that. So we can do that, do all those lines, and then finally you will get this one: 1 plus Z to the power of minus 1 squared divided by 3.4142 plus 0.5858 Z to the power of minus 2. Okay, and always we need to convert this into this. Okay, because let's see about this one. Because what we need to do is finding the filter coefficient. So what is the filter coefficient A here? So what we will have is, this is the first one, 3.4142, and then the second one is a 0.5858. Okay, if you are referring to this one. And what is the B? So B is, of course, you need to solve this. This is a 1 square, and then this is a 1 square, and then the 2z to the power of minus 1, and then z to the power of minus 2. So this is a 1, 2, 1. Okay, so hopefully I'm not wrong. Okay, so you can check that one. But what I'm highlighting here is this value. So what is this? So this is A0. Okay, and actually A0, we should set A0 always equals to 1. A0 should always equals to 1. Because this A0 will be multiplied to yn. And we doesn't want, there's a multiplier to yn. So this is where we need to move this 3.4142 to the front and then up, so that we will get something like this. So then this one will be our A0. Okay, so we need to do that. And by this one, so if you convert that into difference equation, so you will get something like this. So this is a yn. So now there is the multiplier to this yn is 1. So this is actually 1 multiplied by yn. So what is this? So this is A0. Okay, so that's why it is important to make sure that this A0 equals to 1. So we just factorize it. And so we get this one. And in filter design, so actually this has a name. This is what we call filter gain. Okay, so this is actually what we call a filter gain, 0.2929. Right? Okay. So okay, so now let's repeat this example so that we can use this method. Okay, instead of replacing every s with this relationship. So this is what we do now is replacing this s with this thing. Okay, so now let's do this. So because we already know it is a second order, we should solve this one. Okay, we should find B11, B12, B13. Okay, let's do that. So from the table, so we know that Hz is actually equals to 1 plus z to the power of minus 1 z squared B11 with z minus 1 z minus 2. So this is actually just 1 plus z minus 1 squared divided by B11 plus B12 z minus 1 plus B13 z minus 2. Okay, so where do we get this one? From table. Okay, so we just use this table because this table is a standard table. So we have simplified that. Right? So actually, you can find this table in our course only. Normally, you won't find this table in other books or maybe some website. So from website, from books, you will normally find this thing. And then you need to do the original transform. Okay, but in our class, so in our slides, so we have this table, right? Special. Okay, so let's solve this. So what we need to find is just a B11, B12, B13. And what is a B11? So looking at the table. So B11 is, so when it is a B11, so we know that I is actually equals to 1. Right? So, so what is a B11? So it's a C squared plus A1 C plus 1. Right? And what is a A? A is 1.4142. So that's why we need this one. Okay. Okay, then we already know that. So this is a C squared plus A1C plus 1. Hopefully I'm correct. C squared plus A1C plus 1, right? And what is a C? C, we already know it is equals to 1. And what is a A1? A1 is a 1.4142. So then easily we can solve that. B11 is actually just equals to 1 squared plus 1.4142 plus 1. And do that. So this is a 1 squared equals to 1 plus 1 plus 1. So you will have 3.4142. So that's B11. So now let's go to B12. And B12 is equals to, this is a B12 because it is a B12, then we know that I is equals to 1. So this is a negative 2C squared plus 2. Negative 2C squared plus 2, which is equals to minus 2 multiplied by 1 plus 2 equals to 0. And the last one, which is a B13. So, and then B13, look back at this equation. So it is a C squared minus A1C plus 1. So this is A squared minus A1C plus 1. So which is equals to, sorry, this is not A, this is C. C squared. So 1 minus 1.4142 plus 1. Okay, so then this is 2 minus 1.4142, which is equals to, let me do that. So you can do it also, so that we can check our answer. So it is 2 minus 1.4142, 0.5858. Okay, so now we have the three value. Okay, now we're going to replace it into this Hz. So then our Hz is equals to 1 plus z minus 1 square. The first one is 3.4142. And then the second one is a 0. So this one is a 0. So we will have a z to the power of minus 1. And then this is a plus 0.5858 of z minus 2. Okay. Make it clear. So this is square. So, and this is actually exactly similar to this one. Exactly similar to this one. So then you can do the rest. So which is what is next? So you should make sure this A0 becomes 1, such this. So you need to factorize it. So bring this out, factorize this, and then bring it up. So then you get 0.2929. Okay, which is, there is a name for this one. This is actually filter gain. Okay, so, all right, so using this method, so it will be simpler. Okay, especially if the order is higher. And this is just a second order. So if it is a third order, if it is a fourth order, so it becomes easier because we doesn't have to replace every S into Z. So let's see. And this is exactly in exam, you will see this table, right? So in exam, you will see this table. So you are given up to fourth order. So it means that the question is the possibility. The possibility. What will be the question? The question is that the possibility is only up to fourth order only. So it's not possible to ask you on the fifth order, because in table you are only given up to fourth order. Even fourth order is already quite complicated. Okay, so if you look at the fourth order here, so it is a 1 plus z minus 1 to the power of 4. And we have two terms of this second order. So this is the highest power is minus 2. So this is minus 2. So we have two sets of this thing. So because of that, because we have two sets of this power of 2 also here. So this is where the A, so we have A1, which is 0.7654 here. And then this is the second A. So this is A2, 1.8478. Right? So if you're confused, no worry, because the A is already listed here. So this is the A1. The A1 here is 1. Why this is actually 1? Because this is 1. Right? So everything is there. And all the equation, what is a D1, D2, B11, B12, because we have this is a B11, B12, B13, because we have a second set. So this is actually B21, B22, B23. Okay, so we have that. So we have that one. So if B21, so means that this is the I is equals to 2. So then this is a B21, then C squared plus A2C. So this is, you're going to refer to A2 here. Right? So make sure you are familiar with this table, because this is the one that you're going to have in your exam. So doesn't need to memorize anything. So you just need to know how to use it. Okay, you just need to know what is the order. Find C. After you find C, you get C, you can solve everything. All right, so this is what we have. This is yn equals to 0.2929 multiplied by all those input sequence, and then minus the 0.1864 of yn minus 2. So in order to see the shape of the filter, so we need to plot, of course, the magnitude spectrum. Okay, this is the one that we have in time domain. So and this is called difference equation, and this one. This is a H omega, the spectrum of the magnitude spectrum. So we can see that our cutoff frequency is at 0.5, at 0.5 pi, okay? And then because the spec is only giving you a filter order and a cutoff frequency, so it doesn't mention anything, a requirement for this ripple and transition bandwidth. So from that, so we have this kind of filter. And of course, the transition bandwidth is quite wide. Okay, maybe this is a 0.5 somewhere here. So maybe this is 0.25. And it stopped almost at 1. So the transition bandwidth is actually quite wide. So actually very wide for a second order. And another thing here, what we can see that at cutoff frequency now, so the magnitude is a 0.7079. Right? Is that true? Let me check. Sorry, not 0.7079. It's supposed to be a 0.7071. Okay, the what is fixed? FIR, this is fixed at 0.5. IIR, it is fixed at 0.7071. Okay, and we can see that this is the blue line is a second order. So if you increase the order, means increase the capital N value. So the transition bandwidth becomes a narrower and narrower. Right, so this is a 9th order. So it's quite a sharp transition bandwidth. And of course, even the ripple becomes less and less. Okay, so that's in Butterworth's filter, actually, we do control the transition bandwidth and ripples on the capital N, the filter order. Okay, it will control both. So it is actually different in FIR, because in FIR, the ripple is actually depending on window function alone. So different window function will give you different ripple. So it doesn't actually depending on the filter order. The transition bandwidth is depending on the filter order and window function. That one is for FIR. Okay, but IIR, ripple and transition bandwidth, is actually it just relates to filter order. And cutoff frequency at 0.701. So actually this is some difference. So we can see that. So this is omega C for FIR. It is on 0.5. And this omega C on IIR, this is actually at 0.7071. Okay, a difference. Because this one is actually coming from Butterworth's low pass filter. So this is not, and why is it 0.7071? So we know that this is half magnitude. Okay, and why this is not half? So anyone can give some idea here? Okay, because this is last week. So whoever can answer this, I can give you a bonus mark. Because we have learned this from previous courses. Okay, I want to answer that. So why is it 0.7071? Logically, FIR, so we know that this is half magnitude. So but why this is not half? Why this is a 0.7071? So do you still remember from your previous courses? Anyone? You can write on the chat section, or you can speak to your mic. So whoever answered it correct, because we have time, I will give you one bonus mark. 1%. Anyone to try? So you have actually learned it from as early as your circuit theory. Okay, and then you have a signal and system, and then you have electronic system, and then you have a control system. So you have seen this kind of a filter. Anyone want to try? I give you 2 minutes. 2 minutes, whoever can find. You are free. Okay, you have your internet. You can Google, no problem. You can refer to anything. So just share the answer to the class. 2 minutes. So now it's 12:50. I will up to 12:52. A very basic things when we are designing a filter. What the question again? The question is, okay, listen carefully. For FIR, so we are fixing the cutoff frequency. This is cutoff frequency, okay? Sorry, this is the cutoff frequency. We are fixing this cutoff frequency at magnitude 0.5. And it's quite logic because we should have a cutoff frequency because the cutoff frequency at center, right? It's supposed to be between omega p and omega s. And where should be the center? The center is at half magnitude. So that's quite logical. Okay, and this one is 0.7071. So why is not on 0.5? Okay, something to do with minus 3 dB. Yes, it is something to do with minus 3 dB. So why minus 3 dB? So that's actually, you are more familiar with that one. Why minus 3 dB? Actually, this one is minus 6 dB. That 0.5 is a minus 6 dB. This one is minus 3 dB. So why minus 3 dB? So you have heard a lot of that. You should do that. You need to look at minus 3 dB, minus 3 dB. So why is that? What is a minus 3 dB? Why it is so significant?
Quality factor.
Quality factor? Yes, has something to do with that, but why? Why is that? Why we choose that value? Why we choose a minus 3 dB? Why not minus 2 dB? Okay, I'd like to point out that 20 log is actually equals to minus 3 dB, and log is also minus 3 dB. That one is a 10 log, so we should do a
Because it's
20
the
log.
cutoff point.
Okay. If you do a 20 log of 0.5, you get minus 6 dB. But yes, 20 log 10 of 0.7071 is a minus 3 dB. So that one is just converting between magnitude and magnitude dB, so that you get a minus 3 dB. Anyone? Cutoff frequency? Yes, of course. This is a cutoff frequency. This is what we discussed. Why cutoff frequency of Butterworth's filter, which is an analog filter, is positioned at 0.7071 or minus 3 dB. So why is that? This is actually fixed.
Google, it's at the point where the power is half of the maximum value. So we decide that when it's half, that is the point of cutoff frequency. I'm just repeating.
Congratulations. That's correct.
Thank you.
That's correct. So who is that?
My name is Nabil Haziq.
Again, Nabil?
No, I am Umar.
Nabil, okay, I will search for your name later. Nabil,
Umar, Dr. Nick
Umar, okay, Nick Umar, okay, good. Right. So congratulations, you get 1 bonus point. That's actually true, okay, it is true. 0.7071, now we are looking at magnitude. So actually 0.7071 is a half power. How to get power? Magnitude square. If you do square to this one, 0.7071 square, so you will get 0.5. Okay, because in analog system, so most of the systems, so actually you are doing with a lot of hardware. So they are actually measuring power. So that's why the filter itself is actually measured when they decide something. So they need to make sure that it is on half power. So that's the logical decision on how to place, how to position this cutoff frequency. It's supposed to be at half something. So half of what? Half of power. Okay, so that's an analog filter, half of power. But when we do a digital filter design, so actually we don't really involve those circuitry, the RLC circuit, the op-amp. We don't do that. So everything is actually on discrete system. Everything is on memory. So power is not that significant anymore. Okay, when we design it. So that's why it is actually, then we just look at the magnitude. So then, because when we do a windowing methods, so we just take an ideal filter, turn that into an impulse response. And then from there, so actually we are setting the cutoff frequency at half magnitude. So both are actually a logical design because we are actually taking half. So it's just that this is a half magnitude, FIR is a half magnitude, IIR is a half power. So that is actually minus 3 dB. Minus 3 dB is a half power. Okay. So now you know after from year 1 until year 4, so that is actually minus 3 dB. A lot of things on minus 3 dB, the half power. Okay, so any other questions? So any questions? So if not, we're going to end at this example, and then on Thursday, so we're going to look at another example, which is we're going to skip that one, and then we will focus on example 5. Okay, on Thursday, which is our last class. So we're going to focus on example 5. And because this is last week, so I already give 1 bonus mark today. So more bonus mark will be given on Thursday. Right, so make sure you come to the class, the last class. Okay, because someone will get a bonus mark. All right, any question? Last question? If not, we will end this class. Okay, I think no questions. So okay, I'll see you guys back on our last class on Tuesday. All right, Assalamualaikum warahmatullahi wabarakatuh, and good afternoon. So bye everybody.
Waalaikumsalam. Thank you so much, Doctor. See you next class.